This is a tutorial on electron configuration. Electron configuration is the arrangement of electrons in an atom. And electron configuration determines how an atom behaves. It's fairly simple to figure out how the electrons in any given atom are configured if we just follow the rules for electron arrangement. You've probably already had an introduction to the idea of electron configuration using something similar to the Bohr atom, and you probably learned that the first main energy level can hold 2 electrons, the next main energy level can hold 8, etc., etc. We're going to go into a lot more detail now using the idea of orbitals from Schrödinger's work and using some very specific rules for electron configuration. The first rule for electron configuration is called the Aufbau principle, and it just says that any electron will occupy the lowest energy orbital that's available to receive it. 1s, the s orbital on the first main energy level, is the lowest energy orbital that exists. 2s comes next in terms of energy, and then 2p. Then things start to get weird. So let's look at this conceptually first. If you head off to move into a high-rise apartment building someplace, maybe a college dorm in your first year, and there you are carrying all that you own on your back, when you get to this building, you don't want to climb any more stairs than you have to. So, if there's a room on the first floor that's available, you're going to take it. If that's not available, then you'll go to the second floor. There'd be no reason for you to climb all the way to the 4th floor. This is fairly straightforward. So we go from the 1s to the 2s, to the 2p, to the 3s. It's only after that that things get a little bit weird, and we have to use a very special chart to help us remember. This is called the orbital filling diagram, and when we draw this and put lines through the names of the orbitals, it shows us the order of ascending energy, and hence the order that they fill in. It's very easy to do, and you'll get very good at drawing it. Let's practice. To draw the orbital filling diagram, you start with 1s, then 2s, then 2p, 3s, 3p, 3d, 4s, 4p, 4d. On the 4th main energy level, we add an f orbital, so it goes to 4f, 5s, 5p, 5d, 5f. We could go out further, but we seldom deal with any atoms that have electrons in those big, crazy upper levels. 6s, 6p, 6d. Again, we could write 6f, but we very seldom get to any atoms that have electrons there. 7s, 7p. That's about as far as we need to go. Then we draw arrows through on an angle like this, and that shows the order in which orbitals fill. So the 1s will fill first, followed by 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7f, 5f, 6d, 7p. You get the idea. It gets pretty wacky. And without drawing the orbital filling diagram, you'd really have no chance of remembering them. The second rule for figuring electron configuration is called the Pauli exclusion principle, named for the German physicist Wolfgang Pauli, an interesting guy, but that's another story. What the Pauli exclusion principle says is that no 2 electrons in the same atom can have the same set of 4 quantum numbers. So in other words, they can't have the same address. Since there are 2 electrons in each orbital, each must be designated with a different spin. If we go back to the metaphor of the high-rise apartment building, if we have 2 individuals, both in that first floor apartment, in other words, the 1s orbital, we'll have to, if we want to get a birthday card to one of them, we'll have to somehow differentiate it as tenant A or tenant B. So in the case of an orbital, the way we differentiate the 2 electrons in it is with their spin. We would say that in the 1s orbital, One electron is listed as having spin up, the other is spin down. Remember, this is not literal. This is it's particle physics, and it's a little bit beyond what we can do here. But we designate them as spin up and spin down. Okay. The last of our three rules is Hund's rule. This states that orbitals of equal energy are each occupied with one electron before any orbital is occupied by a second electron. So if we go back to our high-rise apartment or dorm building metaphor, if you get to the apartment building and the first floor is all occupied, and the first part of the second floor is all occupied, and you climb the stairs to this set of rooms, and two of them already have one occupant, you're going to go into that third room rather than climb the stairs to the next level. But you're not going to go in with somebody else unless you have no other choice. Now, once there's one person in each of these, rather than climb more stairs, fine, you'll suck it up and take a roommate. But if you have the option to not climb any more stairs and not have a roommate, you're going to take it.
Mama.
Okay, so let's start with actually representing electron configuration, referencing the three rules that we've talked about. So the first way that we'll learn to show electron configuration is what's called orbital notation. In orbital notation, every individual orbital is shown, and an unoccupied orbital is represented by a line with the orbital name written underneath it. Electrons are represented by little arrows up and down to show spin. Let's try it. Let's start off by showing a carbon atom which has 6 electrons. So we start by writing the name of the first orbital and drawing a line underneath it. There's our 1s orbital. We know that there are at least 2 electrons in carbon, so we'll draw 2 electrons in the 1s orbital. It's fully occupied. Now we'll draw the next orbital in energy, which would be the 2s orbital. So we know that there are at least 2 more electrons in a carbon atom, so again, we'll put 2 electrons in the 2s orbital. Now we want to draw the next, what we would call subshell, which would be the 2p subshell. It's made up of all 3 p orbitals that exist on the second main energy level. To differentiate the p orbitals from one another, we usually write 2px, 2py, and 2pz, because the p orbitals are oriented along the x, the y, and the z axis. Now we only have 2 electrons left, and it might be tempting to try to put them both into that 2px orbital, but if we think back to the Hund's rule, we know that no one wants a roommate unless they have to. So we'll put 1 electron in the 2px and 1 in the 2py. Okay, that's not so hard. That is the correct orbital notation to show an atom, carbon, with 6 electrons. Let's try something a little bigger. Let's try fluorine with 9 electrons. So again, we know that we'll start off with the 1s, and we might as well go ahead and draw our orbitals first. So we've drawn all of our orbitals. Now, when we add our electrons, we know that we'll first put 2 in the 1s, 1, 2, with opposite spins. Then we'll move up an energy level. And because 2s is lower energy than 2p, we'll go ahead and fill it with 2 electrons. So we're up to 4 electrons. We have 5 to go. So we put 1 in the 2px, 1 in the 2py, 1 in the 2pz. We're up to 7, 2 more. Well now, since it would take more energy to climb to the 3s orbital, these 2p orbitals will get 2 electrons. So we add a second in the 2px and a second in the 2py. Okay, let's get a little bit bigger. Let's try aluminum with 13 electrons. So again, we'll label our orbitals. Okay, so we've got our orbitals labeled up to the 3 p's. Now, let's start filling. So we get 2 in 1s, 2 in 2s, 1, 2, 3, 4, 5, 6 in the 2p. We've now got 2, 4, 6, 8, 10. We're ready to put some in the 3s, and it fills. And now we have one more electron to go, so it will go in the 3px orbital. That's not so hard. A few notes about conventions when doing orbital notation. Remember that this is a main energy level. This is a main energy level. That's a main energy level. Well, this is also a subshell, this is a subshell, and this is a subshell. There's the 3s subshell, there's the 3p subshell. So you see how these things are divided. A few words about conventions, as I said. Even though we don't have anything in the 3py and the 3pz, we draw all the orbitals that exist in a subshell that we're drawing. If we have any electrons in that subshell, we draw all the orbitals for the subshell. Okay, let's look at a slightly bigger one. Okay, I've drawn everything up to the 3p subshell. So now let's start filling. We have 2 in the 1s. We start the second main energy level with the 2s subshell, and we fill the 2s orbital. We then start into the 2p subshell, and we fill all of the 2p orbitals. We're now up to 10 electrons. We start on the third main energy level with the 3s subshell, and we fill the 3s orbital. We now have 2, 4, 6, 8, 10, 12. So we've got 4 to go. So we know that each of these 3p orbitals is going to get 1 electron. We have 1 left. So the 3px gets... Okay, that's the electron configuration for sulfur with 16 electrons, or the orbital notation. Remember that notation just means a way of writing it. So orbital notation is the way of writing electron configuration that shows all of the orbitals. Let's do one that gets tricky because it gets into the overlaps. We're going to look at iron with 26 electrons. Well, we've drawn all of our orbitals up to the 3p subshell, but we have to remember that something weird happens after 3p. We have to draw this. Remember this? It's from the Aufbau rule, the first rule that we talked about. So we draw our orbital filling diagram and draw our arrows down through, and we realize that after 3p, instead of filling the 3d subshell, we're going to fill the 4s subshell. Then we'll start to fill the 3d subshell. Now, how many orbitals are there in a d subshell? We had 1 in the s's, 3 in the p's, and we have 5 in the d's. Let's draw it. Okay, so now we've drawn in our 3d subshell. And it's still on the third main energy level, but it's a subshell of its own, and it's kind of interrupted by the 4s. So let's start filling. We have 26 electrons to distribute. We'll start off with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That's how we would show the orbital notation for iron with 26 electrons. You'll have some practice to do on your own. Now, let's look at a quick shortcut, or a second way to show electron configuration. The second way that we can show electron configuration is called electron configuration notation. And it's a shortcut from orbital notation, because we no longer draw every single orbital. We just designate the subshells and note how many electrons are in each of them. Let's go back to our carbon atom and practice. So we drew the orbital notation for carbon. If we were to draw this in electron configuration notation, we would just say 1s2, because there are 2 electrons in the 1s subshell, 2s2, because there are 2 electrons in the 2s subshell, and then we would say 2p2, because there are 2 electrons in the 2p subshell. Actually, let's get rid of those commas. They're not necessary. Okay, fairly simple. Let's step through the other examples we did and show the electron configuration notation for each of the ones that we did in orbital notation. Here's our fluorine with 9 electrons. So to show this in electron configuration notation, we would just write 1s2, 2s2, 2p, 1, 2, 3, 4, 5. And that would be our electron configuration notation. Okay, let's go to aluminum with 13 electrons. So again, we write 1s2, 2s2, 2p6, 3s2, and our final subshell, the 3p, only has 1 electron in it, so we would write 3p1. That would be our electron configuration notation for an atom of aluminum with 13 electrons. Let's jump straight up to our iron with 26 electrons. So if we were to write this using electron configuration notation, we would write 1s2, 2s2, 2p6, so we've gotten all of those subshells done, 3s2, 3p6, 4s2, and 3d, 2, 4, 6, 3d6. Now, when you write this, you can go back and reverse the order on these to show them with their other main energy level compatriots. However, the thing to be careful about, if you're writing this from scratch, if you write all of the energy level 3 subshells, you're liable to forget the crossovers in filling order. So you want to go ahead and write them in the order that they fill so that you fill them correctly. That's it. So you've got 2 forms to express electron configuration. Orbital notation, which shows every orbital, (2pz), and an electron configuration notation, where you only show the subshells. Now, in each of these, you are showing electron configuration. The difference is that in orbital notation, you show every orbital, where in an electron configuration notation, you only show the subshells. You'll have plenty of things to practice on. That's it. We'll pick up the last way to show electron configuration next.